All right. Well, welcome this week to our Google Hangout for the Origin OpenShift community. I'm really happy to have here today both Clayton Coleman from the OpenShift team and Colin Walters from the Project Atomic and of OS Tree um, inventor, I guess is what we would call you, the creator of OS Tree, here to talk about Project Atomic, its relationship to OpenShift, the GearD project, and to give us an overview of what all it means and where it's going in terms of OpenShift, and also to sort of hopefully give you an idea of where you can give us feedback and help contribute to some of these projects. So without too much further ado, I'm going to shift it over to a beautiful picture of this diagram that is also Clayton Coleman. So Clayton, go right ahead and dive in.
Sure, sure. So, as Diane described, there's a lot of different things involved when we say Project Atomic, and I'll just real quickly break down what those pieces are, and then we'll kind of go through some of the individual details of them. So, if you're familiar with OpenShift, we've had this concept called gears for a long time, and gears were basically an SE Linux jail and some of the Linux process isolation. And we've had these for a few years. That's what the fundamental technology that we use in OpenShift Online is. It keeps everybody's source code and application processes isolated from everybody else. And so in OpenShift Online, we can have these big, really high multi-tenancy where we've got lots of different people on the same system, and they can't get at each other's stuff. They can host and run their applications. And in Origin, you can do the same thing with your community and have people in your organization can run their code and keep it separate. So over time, there's a lot of things that have happened in the Linux space that have made containers much more usable and have solved really an important problem, and that's been through the Docker project. So Docker has taken a lot of the technologies that a bunch of different people have been working on for a while and put them together in this nice, easy-to-use package. And what they've really added is that packaging aspect. So they've made it easy to say, I want to install all these RPMs, I want to do some custom scripting, I want to download some stuff and set it up a certain way. And then at the very end, you get to take all of that, bundle it together, and ship it out. So it's a lot like a VM image, but it's faster, smaller, and easier to get. And because it just runs on a Linux system, if assuming a lot of the folks who are interested in Origin happen to be Linux devotees, and you can pull these images down, upload them, share them. When you start them up, they really have this feel of this little unit that you can pull down from the cloud, run something, throw it away, iterate on it, push it back out to the cloud, pull it down. And that's great for distributing the kind of applications that we'd have in OpenShift. It's great for sysadmins who want to try something out in a self-contained environment. It's great for ops teams that want to deploy chunks of code and be able to roll them back and have two on the same system at once and get these fast roll forward and roll back scenarios, a lot faster than VMs. And as we look towards the future, the other part of that is process management, and that's systemd. So being able to say, I want to really ensure that these processes in these Docker images keep running over time. I'm an admin on a system. I want to bundle my my monitoring software up in a Docker image, but I also want to make sure that every time the system restarts, it gets restarted. I want to aggregate all the logs, and so that's systemd, which is been part of Fedora for a while, and it's now part of a lot of the other distributions out there have decided to pick it up. So we see these three technologies working together, but what you really want as an administrator is to have a way of running containers really efficiently on a system. And when you want to roll a security update out to the host system, you want to make sure that you can do the security update. And if anything goes wrong, you want to roll back to the previous version. And you want to do that quickly and reliably. And that's where OS Tree and RPM OS Tree come in. It's the idea of being able to do these atomic updates of sets of packages all at once. And so this kind of blob in the middle, Project Atomic, is the intersection of all of these different ways of delivering software using Docker, running it under systemd on a host system that's built with the RPM OS Tree technology. It's very efficient for doing upgrades of the kernel and the core system libraries and of Docker itself. And then GearD sits kind of at that higher level of, in OpenShift, we want to be able to install and link containers together across not just one system, but 2 or 3 or 4. And that's also something that administrators want to do. They want to get some of those tools for dealing with containers in a bulk fashion. And so GearD is saying, let's take all the bits of OpenShift out that allow us to run these across multiple systems. So we'll get to the GearD stuff later. Why don't we start with Project Atomic, and Colin, why don't you give us kind of an overview of what RPM OS tree is and how it can help folks?
Okay, let's see. So start with OS tree. Let's see. Well, let me jump to. Okay, so I have to do screen sharing here. Is my system configured for screen sharing?
Yep, it's Google. It makes it easy. It's a little green arrow.
Can you guys see my screen?
Not quite yet.
Okay. We can see you.
Sorry, 1 second. Let's see, capture. Screen share. Desktop. All right, trying this now. Now can you see my desktop?
Yes, we can. Okay,
great. Yeah, so to build on what Clayton said, a little bit of background. I've worked on base operating systems for a long time, and you know, on lower level stuff. And to me, OpenShift is very high level magic. You know, where I can just git push and my application's deployed and auto scaled and all this stuff. It's really cool. And the way I see it is we're evolving the base system to work a bit more like how OpenShift works from the start. You know, for a long time, virtualization was going to be the thing, and virtualization is nice, gives you a lot of flexibility, but it has a lot of disadvantages too. Like all of a sudden you have multiple kernels involved. If you're writing an app, you need to manage logging, security updates, and so as Clayton was saying, when you deliver applications as containers, like OpenShift is doing, there's a lot less that the application author has to take care of. So if we're getting to this world where we have small application containers that you can dynamically move around and scale, so there's actually a theme behind the Project Atomic name. So in Docker, unlike a traditional system where you install package by package. In the Docker model, you put packages in a base image. You might put packages in further layered images, and you might have customizations on top. The point is that in a Docker container, you get it as one unit, right? And so if we're in this world where you get the apps as atomic units, well, how can we evolve the host operating system to be more efficient and to work the same way? And that's kind of where this RPM OS tree tool comes in. So it's a tool to update that base operating system. So the kernel, you have SSH there. You, of course, have Docker itself. In the host system, we have GearD, we have systemd, and any other kind of shared services between the containers can be updated also as a unit. And we've evolved a bunch of, as Clayton was saying, a bunch of operating system components to be oriented for this model. So to talk about the OS tree level, let me go here. For a long time in operating system updates, on one hand, we've had package systems, which are really, really flexible, very dynamic. You know, you can easily add, remove stuff, update things individually. But they have a lot of downsides. One is that they're not robust against interruption. If something happens in the middle, it can be hard to recover from. Or after you do an update, it can be very difficult to roll back. Whereas there's a lot of image-based update systems out there, and a number of them have a very simple A-B type partition scheme. You just have 2 copies of the OS, you update one offline, and you just switch to it. It's pretty simple, but you lose a lot of flexibility in this model. Like, for example, oftentimes image-based updates mandate you must use a partition of this fixed size, right? So OS tree is kind of in between, because you have a choice of file system and block storage. You can use anything you want underneath it, and you have online updates. But unlike package systems, we give you a complete bootable file system tree as an atomic unit. But a little bit more like package systems then on the left-hand side, we do carry along any state in etc and var. So looking at some image-based systems, they might say all your local state lives in /media state or something like that, a separate partition. That's how Chrome OS does it. Whereas OS tree it's really important to emphasize it feels like Unix, because your SSH keys go in etc, and everything else goes in var. But like image systems, we're not doing any dependency resolution on the client. This is a sort of visualization of the old model on the left-hand side. This is the traditional package model. So when you do an update with any of your traditional package systems, you'll often have two kernels because they won't remove the running kernel, right? But you only have one copy of all of this other stuff. You only have one copy of your binaries in user, one copy of etc, and one copy of var. Whereas in OS tree, you can see, first of all, kernel and user space always come together as a unit. We update those things together, the /boot and user, and we copy forward any changes that are made in etc, but var is shared state that we don't touch. So if you're using an atomic system, one thing you'll really have to be aware of is that, for example, home is actually var home, and the root home directory is var root home, user local is var user local. So all your state lives in var, and whenever we do an update, we make a new copy, and we never disrupt your running system. And so that gives us a really strong ability to do rollback. So that's a sort of quick introduction to OS tree. It's a way to atomically update and roll back that host operating system.
So Colin, can I ask a quick question here? How does
Yep.
it change, or does it change how you architect your applications if I'm writing a web application that's running?
So OS tree is very independent of that. So the idea is, in this new world of Project Atomic, all your applications come as Docker containers. So you normally wouldn't put anything on the host system. We'll probably in the future have the ability to layer some additional debugging tools or performance profiling tools, that sort of thing. But your web applications will come as Docker containers. So the actual Docker storage by default lives in var lib docker. Yep. So each application container gets its own isolated storage space. Actually, I have a slide for that. Let me go back that I skipped. And this is the visualization of the Docker model where you have a base image, you derive images from it, and then so each app gets its own writable container.
Perfect. Thanks.
So we can talk a little bit more about some of the other features that we're adding to the base operating system. So one, for example, is OpenShift has always used SE Linux, and we're enhancing that now for Docker containers. So you have, just like virtualization, you have, it's called multi-category security. So each Docker container, each time you start, will get its own isolated label that will automatically make sure that even though the Docker containers run as root, they're more strongly isolated by default using the SE Linux technology. And that's landing in upstream Docker now. And in the future, in the base operating system, there's a kernel technology called user namespaces that we're going to be investigating, which will allow a lot more flexibility in this level. In addition, there's seccomp filters, which allow filtering the system calls that a container can make and further isolating them beyond SE Linux.
All right. So Colin, why don't I kick over then to the GearD stuff to kind of talk about how this fits in. So let's get my screen shared. All right. Can you guys see my screen? Yeah. All right. So we're going to jump back down to where we were. So we kind of talked about, okay, well, we have this opportunity to have an operating system that can do updates really fast and reliably. And then we talk about, okay, well, how's that relevant to someone who's using OpenShift? Well, if I'm hosting all these containers on the system, as Colin said, I want to be able to use this system, but I also really want to be able to have some tools on the system that make managing those containers easy to use. And so we think about this in terms of, okay, well, we want to have all this great functionality for containers through Docker and the operating system. We want to build the atomic pattern into the operating system. And then we say, okay, well, we want to manage these from an OpenShift side. I want to have something I can talk to on each of these hosts that let me say, add a gear, remove a gear. For anybody who's familiar with OpenShift today, that's the M collective, what we call the node agent, and it's some calls going across an M collective bus, which is really overactive MQ, and we send these messages out, and the particular host that needs to do whatever the action is, add a gear, remove a gear, stop, start, restart, listens. With GearD, it's very similar. We need to have something that can listen on the host and take an incoming request and say, I'm going to go install a gear, remove a gear. But then we want to take it a step back and make it simple for someone to do this from the command line as well, because even administrators need to be able to get in and create containers and remove containers across one system. But if we were going to integrate Docker with systemd, we want to make there to be a real nice consistent API that lets me do things across these hosts. So the simplest possible thing you can do in Docker is you can pull down a Docker image and run it, and that'll download the files, and then inside Docker will start up the process that you defined, and it'll run it. Well, if you want to run that in systemd, you need to create a systemd unit file. And what the Gear client does is it simplifies that down to say, okay, well, we'll go create a template for you that most Docker images are going to look real similar. And the things that you need is you need to tell me what the image is that you use, that you want to create it from. So in this case, this Gear install command that I'm showing in the slide is a MongoDB image, and I want to install it on the local system, and I want to give it the name MyDB. And so in this case, these diagrams before are kind of showing how this would happen is the CLI is going to talk to essentially the Gear agent, and the Gear agent is going to talk to systemd and set everything up for you. So all of these are things that you can go do yourself. We're just trying to make it easy for an administrator from a couple of different systems to be able to do this. And the Gear client looks a lot like the same API calls that, for instance, OpenShift would use. So OpenShift needs to install a gear. A system administrator may want to install a gear. If you break it down even further and you say, well, I'm not even really someone who deals with OpenShift, but I also want to install a Docker image and run it in systemd, and I want to take advantage of an out-of-the-box SE Linux configuration that's secure, and I want to do some simple networking and some simple linking. That's where GearD comes in and says, we can satisfy a lot of those different use cases with a single tool, and over time, as the functionality evolves, we can hide some of the details of how we're going to integrate Docker and systemd more closely. We're going to add new security or new patterns. And Gear, you don't have to use Gear, but it gives you that way of abstracting, having to know about some of the details, and over time you get the benefits of improved security and better logging and configuration. The second half of, I don't really like this slide, I'm going to go to the other one. So the other thing that we really want to show is in OpenShift today, if anybody's created an app on OpenShift, inside your container, you still have to know the remote IP addresses of the other hosts. And in practical terms, for most people when they're building an application, if I've got a PHP app and I need to talk to MySQL, I've got to read an environment variable, and that environment variable tells me what the host name and the port is, and if that host name and port changes, my app stops working. And if you're developing in a local environment, you're typically not doing this, right? If on a local system you're saying, oh, I'm going to install PHP, and I'm going to install MySQL, and I'm going to have PHP talk to MySQL. And what we want to be able to do is to give that same pattern to someone running inside of a container, where it just works on my local system. It also just works in a Docker image. It works when I have a couple of Docker images on my local system, and then it works when I push to production. And so I'll show a demo of this in just a minute, but one of the things that we want to do is take the concepts that are already in Docker, where you have this container and it has its own network address that's isolated from the rest of the system, and then fiddle around with it so that we can say, inside your container, inside your gear, inside your Docker image, whichever way you want to call it, the local address for accessing MySQL is pointing to another container, but you don't have to know about it. So to get this benefit of you have these apps and they talk to these other containers, but it's really fiddly to configure it, instead of doing a bunch of magic inside the container, instead of you having to use an environment variable or use a service discovery system like etcd, even though those are all great ways to solve the problem, make it so that it feels much more natural. If I build a Docker image that wants to talk to MySQL, I just connect on localhost 3306 and everything should just work. So
Can I ask a question, Clayton?
Sure, go ahead.
So we've made it really easy to do the networking, but in a lot of the database hookups, you still need username and password type stuff. Does GearD have a solution for that?
That is a really good question. So having a way for software units to automatically go and generate a set of defaults. So for instance, if I create, I can have a container that runs MySQL, but when MySQL starts up the first time, I want to generate a password, and then I want to use that password every time. So today in OpenShift, we have that concept because you're right, everybody, you want to have a secure connection. You want to have a good password setup. So with Docker, there's this idea of environment variables, and what GearD provides is a way of taking the pattern that kind of works in OpenShift, where we would generate a password for the database, and then we would share it to all the containers so everybody has access. But outside of the containers, nobody else can see it. So it's not hard-coded. It's dynamically generated. We would do that through an environment file, and I'll actually show that in the demo. And I think this is a good time to show the demo because I'd rather always see stuff working than just talk about it. So this is the same demo that we gave at Summit, and this just kind of show the whole set of things working together in OpenShift. So what I've got here is this is a JBoss EAP application. So this is a Java application running on two containers, two Docker containers. They've got a MongoDB backend, and I'm running a Tomcat EWS load balancer. So the load balancer is mod cluster, and it's taking incoming requests that I'm driving to it in the background. And every time a request comes into this app, the app stores that in the DB, and then this app that's running itself is visualizing itself running. So each of these little bubbles that are popping up is traffic coming in from an external source. So I'm going to kick some more load onto the system so you can see these bubbles popping up. But what's really important here is that this is an app that has a DB and a couple of web application servers, and it's got a load balancer. It's a lot like what's in OpenShift today. What we're actually showing here, though, is instead of we're doing this just with GearD, and what I've got set up is I've got a couple of containers configured on the system already, and I'm going to kind of show this as in a cooking show fashion, where I'm going to show you the final product, and I'm going to work back through how we got there. So I'm going to run the start command, and everything's going to fail suddenly.
Because it's a live demo.
That's a demo. That's what happens when you do live demos. Well, I'm going to do this in the background, and y'all can follow along with me as I make all this work. So, so what I can do from OpenShift is I can, the Gear command line is installed on the system, and these are the actual containers that I have running right now. So each of these is in Docker. So if I do Docker PS, you'll see the same containers. And all Gear is doing is I set this up using some of the Gear stuff that I'll show in a few minutes, but each of these containers is a systemd unit file. So I can do system control, status, demo backend 1. Oops. And you'll see that this is, if I'm a systemd administrator, if I've worked with systemd before, I'm just running a Docker command. Let me highlight it. Actually, where's my Docker command? So I'm running this Docker command, and the GearD client did a bunch of setup for me so that everything is, pretty much the defaults that I would want that I can run this container. This is all stuff I could do by hand. I'm just making it a little bit easier to run. So I'm going to start up. I'm going to tell. If you saw from this list, I have this third backend that's not started. Well, each of these containers is wired together using that container networking I talked about. And what that means is that when I start my demo script is unfortunately failing me today, so I'm going to kill my demo script and try this one more time, and then we'll just do it manually if it doesn't work. give the demo script one more chance at.
So each time you run drive load, we're adding another container that's doing the requests?
So what drive load's actually doing is it's just a for loop that's hitting each of these servers. So you'll see the bubbles pop up. I guess I'm going to have to do this by hand today. So so as an administrator, I can come in and I can start up the third. I can come in and I can start up this this third EAP node. And so what will happen is in the background, EAP is starting up and loading, and so you can see the journal spin by. And this is the system out logs that are coming from JBoss. And what you'll see here is that when that container started, it thinks it's on a local network with a load balancer, so it just went and registered itself. The load balancer sees that there's a new EAP instance, and it starts driving traffic there. So now that the war has started up, I'm going to kind of kick into the next set, which is so part of this is I talked about we have a MongoDB instance. People are always asking, well, why is Docker so great? Well, one of the things that makes Docker so great, and I'm sure that if you're listening in, you're pretty familiar with Docker by this point. But if you don't, Docker allows me to create simple script files that bundle together a whole operating system's worth of configuration and installation and treat that like a unit. So what we've got here is an example of, and this happens to be on RHEL 7, but this could be CentOS or Fedora or Ubuntu or Debian or any of the Linux operating systems distributions. And I'm running a series of scripts that is going to pull the public MongoDB repository, and then I'm going to use RPMs. I'm going to install the RPMs from Mongo Inc., and then I'm going to tell Docker that I want to expose a couple of ports, and then I'm going to run the MongoD command using the command line. And so this image, when the script gets run, it generates an image. That image can be pushed and shared across an entire organization, and every time I run it, I'm getting the same bits and running things the same way. So then if I come in and I want to say, okay, well, I've got this image that's MongoDB, and I've got my EAP. I've got 3 EAP instances, but I only had a single MongoDB backend. Well, what if I want to set up a replica set of MongoDB? And with replica sets, you've got to go do this configuration. The server's at maximum capacity. That's the culprit. I knew there was something going wrong. Well, that helps. Okay, so start my demo once more.
So you have too many of the drive load?
Yeah.
What was wrong? Or?
What was actually happening is we've got some mechanisms that make it so that if somebody goes and creates too many things at the same time, it'll kick you out. We want to make sure that each of these little agents running on each of the machines is pretty stable and can work at the biggest scales that OpenShift has to. But one of the consequences of that is we got a little too protective there. So I'm going to run this deploy. So this is what failed earlier. But what I'm showing here is I've got this Mongo replica set. I created this image, and I want to wire that replica set together. And I want to do it in a way that it behaves the exact same on my local system as if it's remote. So the really important part here, and this is, I think, when we talk about GearD and OpenShift and why this matters for administrators, part of it is trying to make it so that these simple configurations of clustered software that need to talk to each other, web apps that need to talk to DBs, load balancers that need to talk to front ends, message queues that need to talk to other applications, we want to have a real simple pattern. And so what we've done here is the gear command knows that it needs 3 Mongo replica sets, and there's some really simple rules that say, hey, Mongo has this really strict requirement that if you want to run a replica set, each of the containers needs to be able to find the other, and it also needs to be able to find each other on a consistent port internally and externally. And if if you're familiar with OpenShift, when we create a container, we expose this port externally, and if we have 10,000 containers on a single system, well, each of them is going to get a randomly assigned port. The problem is Mongo doesn't like that. So with
Clayton, can I ask a question real quick?
Sure.
So what is it the Mongo Docker file that's saying it wants to be part of a replica set?
In this case, no. What I've done is you can create an image that when you start up, it can look at an environment variable to know whether it wants to be in a to join a replica set or not. In this case, what I'm doing is I've got I know that I want 3 of these images, and inside the image, I know that when I get set up, I'm going to go into replica set mode for Mongo. So let me kick over to. I'll show you guys an example of what the Docker file for a replica set looks like. So when you want to run a replica set in MongoDB, you need to pass this replica set parameter. And if you're an administrator and you're configuring, I would install Mongo on 10 different systems, and I would go and I would set up what replica set name I want. But what really matters when you have multiple replica sets is if you're dealing with multiple systems that have multiple you have multiple configurations at the same time. And one of the things we've always tried to get to with OpenShift, and we're trying to do with Docker and containers, is most software, if you can come up with just the right set of configurations, most things will just work in a default manner. And so here, I've created an image that says, hey, when I start up, I want to go into replica set mode. And with GearD, we're saying, let's create a simple, stable configuration. So MongoDB is started up in the background, and if you've ever set up a Mongo replica set, what's showing down here at this bottom line is I'm telling Mongo, I talk to one of the Mongo instances, and I say, hey, you need to go connect to these other servers. Well, by virtue of me setting up this private network, there's this stable configuration. So when I run that command, I'm telling Mongo, hey, talk to 192.168.1.1, 192.168.1.2, 192.168.1.3. I'm running these on my local system right now, so I've got 3 containers starting up in the background, and you can see here that I've got the MongoDB instances are starting to find each other. Well, the way that they're finding each other is because GearD went and wired them up so that those addresses talk to each other. So you didn't really have to have inside the container, your config doesn't have to change. It's just outside the container. So I've got 2 of the replica sets up, and it looks like the 3rd one's down. Well, that probably means that there was just a config problem with the startup. So I'm going to do gear status localhost. So when I created those container images, or when I created those containers, I gave them a set of well-known names. So I can go check, and it says, oh, look, somebody's connecting to me, but I can't seem to connect to my replica set master. So in this case,
and this is using the new systemd features that are in RHEL 7, right? So we're talking to systemd and journald.
Yep. And so if you do, if you've worked with Fedora for a while, you're probably familiar with the system control command. So I can do system control status. I can do that same command that I just ran through Gear through my system control command. So what you're seeing here and what you saw up above, exact same output. One of them is just coming over through the Gear command so that we can offer this consistent set of options. But if I'm a system administrator and I'm on my system, I can see what all's running, and I'm like, oh, I've got all these services, I can go deal with them. Yeah, all of the tools are there, and we want to kind of have that same tool chain all the way up. So in this case, I just probably want to restart the container. So as a system administrator, I'm just going to go and hit that restart command. That's going to stop it and start it back up again. And I can check the status. And looks like it's listening to connections. And it's a very good chance that I can now check my replica set. So one of the things you may have noticed is I was running a command from the host, and I'm passing in this command that I want to run inside the container. So this is something that today in Docker is a little fiddly. There's a number of different ways you can do it with Linux. We've created this wrapper function that basically calls those. So I can jump in and run a command inside of the container. So here I'm saying inside the first container that I created, I want to run Mongo, and I want to tell it to connect to localhost, or the local DB, and then I'm going to run a Mongo shell command. And so that Mongo shell command printed out these 3 containers. Inside the containers, I can see each of the others. The replica set synchronized and was able to talk, and you can see the ping 0 milliseconds because they're all in the same system. And So what this means is I've got this replica set, and inside the container it looks the same way as it does outside of, or inside the container, no matter what systems these containers would be on, they could still use that 192.168. So as that translates out to OpenShift, where we want to be in, the next, where we want to go with Docker is to bring these same features to things like OpenShift Online and OpenShift Origin and OpenShift Enterprise to be able to go and create Mongo replica sets based off of cartridges. They're using these Docker images and have these linking capabilities.
Right. To me, that's one of the most magical things about Docker is because in the traditional package model, when you install a service, it can be really hard to run it multiple times, right? Like if you want to run Apache multiple times, it was always kind of painful. But with Docker, we've taken an exactly identical Mongo image, right, and just instantiated it multiple times, each with its own data store.
Yep. And there's always going to be a case for configuration. If I needed to have private SSH keys that I wanted to put in this image, I'd still need some way to distribute it. And part of we try to take the lessons we've learned from OpenShift, dealing with how do I take software and break it down into units that organizations and developers can easily use and reuse. And Docker really takes us that next step there to be able to distribute out not just maybe the config and the setup, but to distribute out the binaries themselves. So if I run a Mongo image on my local system, I know that I can run the exact same network and file system config in production, and as long as everything's configured properly outside the container just works the same. And down the road, there's a lot of exciting capabilities that'll come to containers, things that people are used to in the virtualization space. So you can do things like snapshot and live migrate of a VM across hosts. Well, there's people in the Linux kernel who've been working on this for a long time to be able to do the same thing for processes. And there's a couple projects out there that may take a few years to reach full maturity. But doing things like taking a container and snapshotting it on one system and live migrating it to another system, and being able to decouple the network config inside the container is a big step, because then I can just move it to the other systems, update the links, and everything just starts working. So for OpenShift folks, images are great. You can build this image and ship it the same one everywhere. There's really another part of images that's important is if you go to an image model, you still have to deploy security updates. And there's really two ways to do that. You can start up the image, install new updates in it, and create a new snapshot of the image and distribute that snapshot out. One of the challenges is that at that point, you are modifying the image, and you can't go back to that base state and rebuild. And you're doing an update on top, but are you really sure that everything is still built the same? And just like Atomic and the patterns in OS tree, a lot of the patterns for images is you want a repeatable process for building an image from source code and taking that source code and then distributing it as an image. So if a security update comes out, if, for instance, I don't know, there's a huge bug in OpenSSL that everybody in the world needs to update, you still need to rebuild the base images to pick up the new security updates. And then you want to be able to say, take the source code that I have and build it on top of that base image. This is, in OpenShift, we have cartridges today, and cartridges take source code and combine them with binaries, and you get a runnable gear. You still need that concept in Docker. And so we've been working through how do we make that concept kind of generally applicable for Docker images. So I've got this command here, and we call this the build command. It's taking a source from a Git repository, and it's combining it with an EAP image. And really the thing that Docker doesn't have today that we're trying to work and figure out how we can do this the best way possible is I want to use the previous version of my image, all of the binary artifacts, the Maven dependencies, the generated class files, and I want to be able to do an incremental build on top of that. And of course I'm going to get an error.
Because you were just going to show me real magic there for a second.
I was going to show real magic, and the real magic just goes away.
There's a lot of high-level stuff going on there, right?
Yeah.
Let's see if we can try this one more time. If it doesn't work, I'll give this one up to the...
Oh my God.
Yeah, cannot start container. Well, let's do a quick debugging.
Redirect.
This one, maybe my Docker system. I hope my Docker system's not hosed. I still have some space available. Well, I think the demo guides have struck, and I won't be able to show this, but what that does is this will run an incremental build and generate a new image, and it pulls the stuff from the other images. And this is part of a project we're calling Source to Images. We want to work with the Docker community and work with upstream to kind of find the things that make it easy to start from a base image and add source, and then build a final image that I can go deploy everywhere. But then when I want to update again, if a security update comes out, take that base image and my previous image output and combine those together so I don't have to pull down my dependencies again. And so if that, go ahead.
Clayton, I just had a quick question. So you were building a lot of high-level tooling here with GearD, and then OpenShift is going to build on top of that, right? But
Yep.
You're also trying to build a good API. So if I was an organization, I wasn't quite at the OpenShift level, and I wanted to drive GearD like with Jenkins directly, that's something I could do?
Yes, and that really is really important to us, is separating out. Everybody who's used OpenShift or has installed OpenShift it really makes a lot of assumptions. We kind of control the whole stack, and we want to stop doing that. Really, we want to have Docker as a base and systemd as a base, and build some simple patterns around that, and expose an API that we can use as administrators or orchestrators at the OpenShift level, or in an organization who's got other orchestration tools that they're familiar with, and offer these, try and build some composable pieces here. So you can use Docker for a lot of things. You can use systemd for a lot of things. You can combine them together in this one way with GearD, and then the API that GearD exposes should be simple enough that we can build patterns on top of it. And so what I was doing right there is I was just installing, assuming the build had worked, I would have installed that image on top of my existing backend. So I would have updated the backend image and then done a restart of it, and you can see that the journal command is running in the background and these containers are starting up.
So Clayton, let's say I push something to the Git repository, but something goes wrong. Is there a way to build an earlier commit, or should I revert the change on Git master?
So we definitely think that's being able to build from any commit is real important. And the example I showed was just pulling master, latest master. But there are a couple of commands that are available. I think they're available today. Let me do a double check. I don't know if we actually... Oh, yeah, we do. It's right there. So what you can do is when you pull the Git repository, you can also specify an optional reference.
Okay.
And we also, the Gear build is pulling from a source URL, but that source URL could be a zip on the local system. So for instance, if you have a Jenkins flow and you've already checked out the Jenkins source or combined it into a set of things, you could run the Jenkins flow and then pass a directory in to the Gear build command to help generate an image. So really trying to make sure that we have all of the individual tools that a developer would want. And we don't want to enforce things that not everybody in the world necessarily would sign on to. If you're an organization that's made a big investment in Jenkins, we shouldn't have to change the whole world just because Jenkins solves your problem for you.
So, Clayton, can I ask a quick question too? Like right now, what is the state of GearD? Like, do you want people to go to the GitHub repo, download it, play with it, give you feedback with your documentation? What is it that you're what can we play with today? I mean, you're showing us a wonderful demo, but this is where I think the next step is here.
Sure. So let me jump into the download now button. So if you go to openshift.github.io GearD, we have packages available for Fedora 19 and 20, Rawhide, and in EPEL for RHEL 7. The source environment you can build in a VM. So we have a Vagrant VM set up that you can use to pull, you pull this VM down, and we have a bunch of scripts set up so that it automatically sets up your development environment. If you're not a Go developer, or if you just want to try this out, but you want to try out master, we've got a lot of that set up on the website, and it's a very early alpha. So to treat GearD like, we want to prototype a lot of ideas and get a pattern and get those in front of people who are trying to solve real problems. If I want to orchestrate these containers, I want to be able to do these repeatedly. I want to integrate with systemd. There's a lot of work that's going on in Docker right now. Docker just hit 0.10. They're working really hard to get to their 1.0 release. And one of the things that is really a big focus for us at Red Hat is for their 1.0 release, we really want to make it so that administrators on any production system can feel confident about running Docker images and Docker containers, both in their security and their reliability. So we've been working a lot with the Docker community to do things like get a device mapper backend into Docker, which is something that we feel that that big enterprises can rely on. Some of the early stuff in Docker was based on unsupported kernel patches that were carried against the kernel, so you had to it was shipped with Ubuntu and a few other distributions, but the kernel maintainers weren't carrying along. So we said, well, we want to give people an option that may not have all the features that that they can trust in a production environment, and do the testing and make sure that we have a nice stable surface that everybody can develop on. So as Docker gets closer to a 1.0 status, we want to be right there and ensure that Docker out of the box works cleanly. And then GearD as kind of an alpha is a way of using Docker in a particular fashion. There's going to be a lot of evolution of GearD over the next few months. As we bring more of the OpenShift folks in and are looking at different problems, we want to experiment with GearD on its own, but then also experiment it with OpenShift and say, can we test and validate that the things we want to do with OpenShift, the directions we want to go, the features that we want to offer up to the users of OpenShift, what kinds of things can we add to GearD to make that possible? So I want to kind of close with, I think that's a great way to lead into this last one. So one of the things that we also want to do is, GearD is about running containers and helping you link together containers to kind of form a simple application. The build command allows you to build, source, and develop. What we really wanted to do is say, okay, well, that sounds a lot like OpenShift itself. We've got the OpenShift broker, which is a Ruby on Rails app, and it needs to talk to a Mongo database, and then it's got to go talk to these nodes. Well, on this system, I've got Docker, which can run MongoDB, and I know that I can run a Ruby app in a Docker container, and I want to talk to a system that has GearD installed. So I've got an installer here that's going. What I just did was I set up two containers, an OpenShift broker and a DB, and I wired them together using that linking feature we talked about. You'll see in the back end that OpenShift started up, and now it's listening for web requests. I'm actually going to run a script that we've kind of put together in the upstream branch that lets us import a Docker image as a cartridge. And then I set up this local machine as a node for the broker to talk to. And what that means is I can run RHC setup, I can configure my client, I can create a namespace, and I can go create an OpenShift application against OpenShift running in a container on my local host that's also running in a Docker container. So if I do gear list units, I'll see I've got this Docker image running on my system. This application that I just created through the OpenShift running on my system, I've created an image through it, and I can do all those same things that we showed earlier, like showing the status of the app or of this gear. So I can do status.
So this is going to completely change the way and simplify the way we can install OpenShift anywhere.
Yeah, and the goal really is to build on the same patterns that we want to build into the apps, so that we have a real concrete use case. We can simplify installation, and in the biggest deployments, yeah, you may not want to do installation this way. Like Puppet still has a part, Chef and Ansible, and all these different tools still have a part of running big production workloads. But we really did want to get to that point where in a development environment, I can build the OpenShift broker from source code, run it as a container on a local system, and then iterate against MongoDB running in a container. And so we're trying to draw this together so you can think of GearD as a substrate with which you can do container and development in containers and linking containers and running containers, and then OpenShift is just consuming that functionality above it.
Well, make doing a POC or a pilot of it ridiculously simple.
Yep. Down the road, we really want it to be a one-liner on any Fedora system to yum install GearD, or any Red Hat based OS, and even down the road things like Ubuntu and Debian and others to be able to run yum install or apt-get, or just download the binary and then run a one-line command that'll pull a couple of containers down and configure them and wire them up so they just start. And you'll see this over time. There's some work going on right now that you may have seen on the public dev lists talking about we want to simplify the development environment around Docker. Jessica did a bunch of work to get, Jessica Forster has been doing a bunch of work to get our development environments Dockerized, and we're really trying to bring this to the public community in a way that, we have a workflow that works just as well for OpenShift Origin as it does for any of the teams that are building on top of OpenShift Origin. VMs and being able to spin stuff up really quickly, run it in Docker images, and publish those Docker images out to the cloud.
Yeah, I mean, one thing you have to say with Docker is it's so much faster than virtual machines, right? I mean, many years ago when EC2 was introduced, I thought it was really cool because you could actually have your server code spawn more servers using the EC2 API, right? But in here, we have OpenShift as a container running other containers, but it's really, really fast, right? It's not like we're booting a whole machine. We can say we want another Mongo, and it just kind of comes up as almost as fast as starting a process.
Yeah, and that really that speed is what's really important to developers. If you're actively working on something and trying something out, the faster trying that thing out is, the more productive you are. And so I think it's only natural that we really want to keep that focus on. Docker really gives us this ability to spin up these environments really quickly. And how do we as a community and a project, use this ourselves effectively, but then enable the developers who find benefit from platform as a service today to be able to also get that speed advantage, to get these local workflows that are efficient. And there's lots of, it's not just Linux. There's a lot of work that the Docker folks are doing to be able to run Docker on Windows machines through a simple VM setup that kind of just works like you expect it to. And we fully expect to see Docker spread into a lot of places where I may still have a kind of traditional development workflow. If I'm developing a Java app in Eclipse, I might still use all the tools in JBoss or Eclipse to build my WAR file and push it off to a remote system. But I think over time, what you'll see is you'll have more options about, for instance, if I want to push into a Docker image that's running in a VM on my local system, or if I want to push Delta changes out to an OpenShift instance that I'm running on my Linux server in my local lab, or I can make changes and then push them out to OpenShift Online or to an OpenShift Origin deployment I've got on AWS. So it's really about opening up the options for how you can get these little mini environments all over the place.
Cool. So jump back to your slide deck and throw up the last slide about where they can find all the references.
Yeah, let me jump to the end.
And really, we've gotten a lot in this 1 hour. So I really want to thank you for coming together and doing this. There's a lot of information here. You can get more information at projectatomic.io and dig deep there. There's information on the OpenShift Origin community site at origin.openshift.com. You saw the GitHub pages. There are a number of very good blogs that have been written on the topic already on the OpenShift site. And there's information on Docker. You can definitely reach out to Twitter at Project Atomic and get more information about what's going on there. And as always, you can find information about OpenShift at openshift.com or tweet us at OpenShift. And as well, we're always on IRC, whether it's in Freenode on OpenShift-dev or on just OpenShift itself are probably the two easiest ways to get a hold of us. So I really want to thank everybody for all their time today, and we'll post this very shortly and put some more links in, and hopefully we can get some community feedback and testing on GearD, and we'll be following along with more updates from Project Atomic in the coming months. So, Clayton, thanks. Colin, wonderful to see you again, and looking forward to more good things. Thanks so much.
Yeah, it's a lot of fun. Thank you.
Thank you. Bye, guys.